Okay, Assalamualaikum. Good afternoon. Can you guys hear me? Okay, good. Okay, apa khabar semua? Sihat? Boleh dengar kan? Okay, ah. Semua dah makan? Lunch? Okay, hold on. Yeah, let me just approve a few more. Alright, okay. Sound clear? Okay, ah. So, ada orang yang tak dengar tak? Semua okay kan? Loud and clear, right? Okay, alright, that's good. Yeah, alright. Before we continue, I would like to pause a little bit. For your friend. Kenal Syazwani, tahu berita tentang Syazwani? Syazwani baru ada tahu So let's just pause for a bit and sama-sama kita sedekahkan Al-Fatihah untuk arwah ayah kepada Syazwani yang baru saja meninggal dunia pagi tadi ya. Saya baru diberitahu oleh Syazwani dan dia on the way balik ke Kelantan balik Kelantan. So Al-Fatihah. Okay, sama-sama kita doakanlah insya-Allah semoga roh kepada ayah Syazwani ditempatkan bersama orang-orang beriman, beramal soleh insya-Allah dan dipermudahkanlah segala urusan dia selamat balik ke kampung untuk urusan pengkebumian. Okay, so let's continue for today. Let me share the content. Okay. Hold on ya. Okay, all right then. Can you confirm? Can you see the slide now? Boleh nampak slide? Okay, good. So, all right then. Last time we have discussed up to PN junction bias, and we have stopped. We have stopped somewhere. So we've stopped somewhere here near the forward bias uh, calculation of uh, carrier density, right? Carrier density at the edge of depletion region. At the edge of depletion region. So, so let's revise the schematic diagram again. If you look at this diagram here, down here, bottom right, bottom right, this one. Mm, hold on, somebody's joining. Okay, if you look at this, so we stopped somewhere here last time. We have discussed until the calculation of a minority carrier density in the opposite region. So that means when you have diffusion after the bias application, so that means the moment you apply forward bias, so that's going to cause your majority carriers in both sides, P side and N side, to start diffusing again, right? So due to that, due to the diffusion, we need to know what is the density of the minority carrier on the other side of the junction. So to be exact, at the end of the depletion region, given by this point A and B, right? So we want to know now what is the concentration of NPA and PNB, right? Due to the diffusion of electrons from N side to P side, right to left, and also diffusion of holes from P side to N side after the application of forward bias. Okay, we know that the concentration is going to change, and now we need to check how much does it change. All right, so let's look at this slide now. At forward bias, using superposition model, both drift and diffusion currents are large and opposing in the depletion region, opposite direction. So at moderate bias, the net current flow is a small difference between these two much larger values. So this can be approximated as drift is approximately equal to the diffusion. Diffusion current density is approximately equal to drift current density. Okay, so let us go back to the PVCD-ROM to see a little bit of animation before we move on. Let me share with you the page. Where's the page? I think this is the page. Yep. All right. Can you see this PVCD-ROM page now? Can see, right? Can you see? Oh no. Okay, not. All right. Let me. Oh, not yet. Okay. Let me redo again. Okay. Hold on a sec. Share content. All right. Okay. Let's go back to this. Participant. Hold on, yeah, still joining. Chat. All right. Okay. So let's recap a few things. You can now see the page, right? Now I can. Okay, good. Okay. Okay. So let's recap a few things before we move on. You look at this. Semiconductor devices have three modes of operation. We have discussed this one last time before we move on. So let's recap: thermal equilibrium, steady state, and also transient. Transient is something new that we want to mention here. So thermal equilibrium we've discussed last time. There a condition where there are no external inputs such as light or applied voltage. Um, the current balance each other, so there's no net current within the device, right? So next one is steady state. Under steady state, there are no external inputs. There are external inputs, sorry, such as light or applied voltage. It could be some other means of forces from the outside, but the conditions do not change with times, right? So this one is a steady state. So devices typically operate in steady state and are either in forward bias or reverse bias. So as long as there are something, but it doesn't change with time, so that's considered a steady state. And the third one is transient condition. Transient is, for example, if the applied voltage changes rapidly, then there'll be a short delay. This one is for solar cells, so the explanation is more specifically towards solar cell. But the idea of having transient is that you apply illumination or applied voltage just for a short time, and then you turn it off and then see what happens to the devices, right? So this one is just a recap. So let's see this one, the animation below, before we move on with the forward bias and reverse bias condition. So this is just to animate the effect of forward bias and reverse bias. So we start off with thermal equilibrium first. So you can see the movement, right? Right. This one is in thermal equilibrium condition. So what do you see there? What can you see from there? Thermal equilibrium condition. Anyone? Do you see electrons and hole crossing the junction? Yes. Yes. Do they supposed to cross the junction? Are they supposed to cross? Sorry. Okay. Well, in principle, they're not supposed to cross the junction, right? Right or not? Kenapa at equilibrium they're not supposed to cross the junction? Let's recap before we move on. Anyone? Kenapa they're not supposed to cross? But you do see some crossing. Same concentration. Yes, on both sides, already same concentration. Okay, any other answers? Why they're not supposed to cross at thermal equilibrium? Agak sebab apa? Kita dah belajar kan, thermal equilibrium they're not supposed to cross, right? Because of Farah, any idea? Different charges. Yes, different charges at the junction. So therefore, kenapa they not supposed to cross? Let's recap. What happened at thermal equilibrium? Yes, potential barriers, right? So potential barriers due to the different charges on both sides. So they are now not supposed to cross the junction anymore because they can cross the barrier, right? But now we do see some of them, little, not majority, are still crossing the junction, right? Agak-agak sebab apa? Why do you think so? In principle, they're not supposed to cross, but they are now crossing. Ada tekan ke? Any guess? If you see there, the blue one, the blue is hole, red is electron, blue is in the blue region, red is in the red region, but occasionally you see some reds crossing the junction and some blue also crossing the junction. Any idea? This is called, an idea. So this is called leakage. Leakage current. Let me type down. Leakage current equal to J naught. So it's equal to J naught. Leakage current density. Nanti kita akan belajar ideal diode equation. Ada belajar tak ideal diode equation dalam other courses sebelum ni? Ada belajar? Oh, belum ada. Alright. Have you seen any IV curve of a diode? Pernah tengok tak any IV curve of diode? Belum Alright, that's okay. We're gonna see it after this. Right, so this is thermal equilibrium. So holes supposed to be held in p-type, electrons supposed to be held in n-type by the potential barrier in the depletion region due to the presence of the space charge region, right? SCR. So you're going to have electric field, you're going to have potential barrier. So these are going to hold holes in p-type, electrons in n-type. Therefore, they are not supposed to cross the junction at thermal equilibrium. However, we do have some of them still crossing the junction, and this is called leakage, right? Leakage current. Nanti kita akan tengok. So let's now look at the animation of forward bias. So if you see in this thermal equilibrium now, before we move on to forward bias, there's zero voltage across the diode. There's no current flow due to this phenomenon, right? Now let's look at forward bias. Any difference do you see now? So we are now applying forward bias. So that means the positive terminal is connected to p-type and negative terminal is connected to n-type to make the junction forward bias. So you need to apply some voltage, some bias across it. So what do you see now? In terms of the carrier movement across P and N regions, do you see more? Do you see more carriers moving around, diffusing around compared to the previous condition? Yes, right? More carriers. Kenapa you see more carriers now at forward bias? Let's just recap first. Why do you see blue crossing to n-type and electrons crossing to p-type? And you can even see some electrons flowing through external circuit to complete the circuit. So why do we see more carriers diffusing around now, moving around? Yes, Eliana, lower potential barrier. What makes the potential barrier lower? Yes, Jasmine. All right. Okay, smaller potential barrier, smaller depletion region. Good answers. Right. Smaller PB. Fazira, PB stands for what? Potential barrier, right? Yeah, good. I know it's potential barrier. So what makes the potential barrier lower? What pushes the potential barrier to be lower now? Kenapa dia jadi low? Right? Because you're applying you're applying a positive to hole side and negative to end side, and then same charges repel. So you're pushing carriers towards the center of the region by the applied bias, right? By the applied bias. So what causes the barrier to reduce is actually the applied bias, right? So the moment you apply the bias under forward bias, so you are actually reducing the effective electric field at the junction. So electric field you apply is actually opposing to the built-in electric field at the junction. So therefore, electric field, effective electric field will be smaller than the original condition in a thermal equilibrium. The same goes to the potential barrier. So the moment the field is effective field is reduced, you are actually reducing the potential barrier as well. So therefore, holes can start diffusing again into n-type, and electrons can start diffusing again into p-type, and they can even complete the circuit now, right? So now let's go to the third condition. So now this is reverse bias. So reverse bias is achieved when you connect negative terminal to positive side to p-type and positive terminal to n-type. So what do you see now? Ada carrier crossing around? It's more or less like thermal equilibrium, right? Yes, Ishin. So it's more or less like thermal equilibrium, but you can still see a few, right? You can still see a few of the carriers crossing around, just more or less like a thermal equilibrium condition. So this is also leakage current. It's also due to leakage. So the current arises from this leakage is called leakage current. So we're gonna see in IV curve later on the magnitude of leakage current under reverse bias condition. Okay, so you can later on go to this page, PVC DROM, and see the explanation for this under forward bias and reverse bias to be able to know the explanation more, right? So now let's go back to the um slide. All right, so you can now see the slide, right? Right, can you see? Just to confirm before I move on. All right, that's good. Saya tak nak saya continue tapi tak nampak nanti saya cakap sorang-sorang pula. Alright. So you want to calculate NPA and PNB. So that means these are the values of minority carrier densities in the respective region. So hole in N-type region, electrons in P-type region, right? So you can go through the derivation here, right? But the most important thing now that you have to look at after the derivation is this one, the below one. PPA, PPA in this equation can be approximated. PP is here, the top one here, top left, is actually the majority carriers, right? PP, P in P, density of holes in P type. So NN is the density of electrons in N type. So that is approximated as follows. PP naught, PPA is equal to PP naught is also equal to Pn naught exponential Q VBI, this size VBI over KT, right? So you can actually estimate PPA from there, right? So let's move on to the summary on the next page so that you can see the equations for all conditions. All right, so this is the summary. Okay, so what you have to know is actually these two things, PNB and NPA. So which is if you look at the previous slide, is actually the minority for the first one here. PNB is actually density of minority hole in in n-type region, right? On the n side, on the other side, okay, at point B. So that means at the end of depletion region, okay, at point B. Remember the border A and B, and this one NPA is given by density of electrons in p-type at point A at the other end of depletion region. Okay, so that means now you want to know the starting concentration of the minority carrier right after they cross the depletion region. Okay, so nanti kita akan belajar to calculate the density of minority hole and minority electrons in the quasi-neutral region, right? Quasi-neutral region. So if you look at now, okay, let me just draw something. Okay, so the central region is actually the depletion region. So it's given by A and B, right? A and B. So this is your, for example, your hole concentration. So let's say this one is P side, so therefore the majority carrier is hole. So the moment you apply the VA, the applied bias, forward bias, so the holes are going to diffuse again, right? The same goes to electrons on the other side. So the moment they diffuse across the junction, you want to know what is their concentration at this point, right? Kita dah tahu dia punya majority kat sini, then they cross. You want to know what is the concentration at this point here. You need to know this point because later on you need to calculate what is the concentration further into the quasi-neutral region of n-type, right? N-type quasi-neutral region, right? Q and R. You want to know the concentration of the minority hole in the neutral region or quasi-neutral region to be more accurate, right? Same goes to n-type as well. You just can draw something like this, and you want to know what is the starting concentration here at the end of the depletion region, so that later on you can calculate the concentration into the Q and R as well. Okay, so this point and this point is given by PNB and NPA, right? So PNB is given by PN naught, PN naught. What is PN naught? So can you redefine PN naught before we move on? Anyone? What is PN naught? Three things, right? Remember three things. Density of hole at thermal equilibrium in in n-type, right? So density of hole in n-type at thermal equilibrium. So if you compare this PN naught dengan PNB, apa beza dia? What do you think is the difference? So PN naught, if you define again, density of hole, which is minority carrier now, in n-type material at thermal equilibrium. So if you define a PNB, density of hole in n-type material at point B, right? But is PNB now at thermal equilibrium? Is PNB now at thermal equilibrium? No, no, right? So that means PN naught is for thermal equilibrium. PNB after you apply the positive forward bias, right? After you apply the forward bias. So that means after you apply the VA. So tadi kita tengok dalam animation, bila dia kat thermal equilibrium, so most of the carriers are held in their own region, right? So we only have a few crossing the junction causing the leakage. But the moment you apply positive bias, you can see they start crossing again, right? Due to the bias yang menyebabkan barrier reduce. So now we want to know the PNB versus PN naught. So do you expect PNB to be higher than PN naught or lower than PN naught? Based on the animation. So bila kita apply forward bias, do you expect PNB to be higher than PN naught or lower than PN naught? Higher, right? Yes, Naim, good. Higher, because tadi kita nampak bila you apply forward bias compared to thermal equilibrium, kita nampak more carriers crossing, right? So the moment you see more carriers crossing, by logically, Kalau you measure carrier density dekat end of depletion region on the other side, so you should be able to see more carriers, right? More carriers yang cross the junction as minority carrier. So therefore, to be able to know the exact carrier density at P and B, you need to base on P and naught first at thermal equilibrium. So you get P and naught exponential QVA, which is given by your applied bias over KT, right? And that's also equal to P and naught is given by your Ni squared over Nd back to your law of mass action, Ni squared over Nd given by dopant concentration in N-type. In N-type, remember? Sebab kita sekarang we're talking about N-side, right? Pn, so Pnb. So in N-type, so therefore, kita nak tahu dia punya minority carrier concentration in N-type. Exponential QVA over KT. And the same goes to NPA. NPA at this point, left hand side. So that has to base on NP naught. So sama juga. NP naught, density of electrons in p-type at thermal equilibrium, and NPA is density of electrons in p-type at point B after the application of forward bias. Right? So sama juga, you kena kali dengan exponential of QVA over KT, and that's also given by Ni squared over Na times exponential QVA over KT. So based on this calculation, after you do the calculation, you should be able to see higher values of NPA and PNB versus thermal equilibrium values, right? So you can see here from the schematic down here, the graph down here. So P is on the left hand side, N is on the right hand side, and then you can see due to the application of VA here, the carrier concentration increases at the end of the depletion region, right? So the higher the VA, the higher your PNB and NPA, right? So hole density on the other side of the junction, that is edge of depletion region on N-type, depends exponentially on applied bias voltage VA. And the same goes to electron on the other side as well. Okay, this increase of hole density in N-type or electron in P-type is known as carrier injection. So last time we have also learned about carrier injection, right? Still remember how can you do carrier injection? What are the methods that you can use to do carrier injection? So remember, this is one, applying bias. Apa lagi kita nak boleh buat to be able to increase carrier injection? To add on carriers to the thermal equilibrium values? Recall? What else can we do? Yes, doping. Yes, you can do doping. What else? Sekarang kita tengok kat sini, applying bias. So you can do carrier injection. Then you can dope. You can increase carrier injection as well. What else? At least one more. You can also shine light, right? You can also illuminate your semiconductor, and then you can then increase your carrier injection, right? Still remember the equation for the carrier injection? Just put it down. So if you're talking about hole, then it's your P naught value, your thermal equilibrium value, plus your delta P, which is your new carriers, right? Your new carriers, your excess carriers. And the same goes to n as well. So that's given by n naught plus delta n, right? The delta can come from forward bias, doping, can be illumination as well, right? So in this case, we're talking about forward bias, which contributes to your delta n or delta p. So it's called carrier injection, okay? So if you look at the question down there, how does the hole, that is the minority carrier density, vary across the N region? So sekarang ni kita dah tahu kalau you guna equation ni, you can calculate, let's say P and B. So you know the P and B here, for example, at point B. So you know the P and B, N and B. So, and that's given by P N naught times exponential QVA over KT. So how does your whole here vary across the N region? So it's talking about this whole region, the whole curve, sampailah kita habis the whole PN punya block, right? Why do you think it's important to know the minority carrier across the N-type region? Why do you want to know this? Agak-agak sebab apa you kena tahu benda ni? Remember last time we discussed about the diffusion length, right? If you have a junction, for example, if you have a device later on, you'll put some contacts on the N-type, some contacts on the P-type. So on the right is N-type. So katalah you letak kat sini aluminium, for example. Aluminium, and perhaps this side is aluminium as well. Contoh ya. So you want these carriers, these minority carriers, in the Q and R region to survive until the contact. Right? You don't want them to recombine. So therefore you can roughly estimate how much do you still have at the contact at this point, right? At this interface between semiconductor and the contact, and also this, and also this interface for the electron minority carrier, right? Kalau let's say you ada contact, but then your profile goes down like this, let's say it goes down to 0, sini dah recombine semua, then do you have anything at the contact? Do you have anything at the contact? You have nothing at the contact, right? So you have nothing at the contact, therefore you have no results. So if you are fabricating a device based on a PN junction, but your minority carrier survive on only until this point and it doesn't get to the contact, so you won't get anything measured on your whatever IV curve, so you wouldn't see anything, right? So is it clear so far? Are you clear with right? Okay, Afaika, okay. Anyone not clear with the effects of forward bias to the minority carrier on the other side of the region? Any questions so far? It's 3:40 already, so fast. Okay, semua okay? You can look through the derivation, but the most important point is this equation up here, right? PNB and PA, which is given by these two equations, right? So conclusion is, if you apply forward bias, you will increase the density of minority carrier at the end of depletion region, right? So if you're talking about holes, you will find more holes at the end, at the site of depletion region in N side, and also you'll find more electrons at the end of depletion region on P side, where they are now minority carriers. Okay. Okay, let me look at the next one if we still can continue. Okay, perhaps we'll finish off this page. So minority carrier flow in N-type region, it can be shown that minority carriers in the uniformly doped space charge neutral or quasi-neutral. So this quasi-neutral is actually referring to the this region, Q and R, or also this region, Q and R. Yang luar depletion region, to the left and to the right of depletion region is called quasi-neutral region. So they are predominantly found by diffusion process, because the moment you apply your forward bias voltage, so they're going to diffuse again, crossing the junction, and they'll be found on the other side due to diffusion. Thus, due to this, in N-type, on the right hand side, the Q and R, the current contributed by this diffusion process is given by the diffusion current density, as we have learned last time. So which is given by negative QdHdPdx, right? QdHdPdx, right? Diffusion down a concentration gradient, and the same goes to the other side as well. Let me see, what do we have on the next slide? Okay, I'll just stop here first before we move on to the next one. Yeah, perhaps we're going to finish this Wednesday. Then we're going to move on to to the next one, which is PN junction by illumination. Okay, any question for today? Is it okay? All good so far? Okay, that's good. Nanti saya akan upload the online punya kelas ni on e-learn just as usual. So don't forget your attendance. If you have any problem with attendance, let me know. I'm still using the multi-session thing. If it's not working, yang Dr. buat kesimpulan tu laju. Okay, kesimpulannya, let me recap again the conclusion. Conclusion for today, we started off with thermal equilibrium, and we found out that the carrier stopped diffusing. Okay, stop diffusing due to potential barrier, due to electric field at the junction in the depletion region, right? So then we applied forward bias. So application of forward bias akan lead to reduced potential barrier due to opposing electric field by the bias. Therefore, your barrier reduces. Then you're going to start seeing more diffusion of holes into n-type, and also more diffusion of electrons into p-type. Okay, so due to the new diffusion by the forward bias, you will see higher concentration of holes at the end of depletion region on n side, and you will also see more electrons at the end of the depletion region on p side, and that's given by just now the PNB and NPA. So PNB, okay, due to the applied bias, PNB is higher than PN naught, and also NPA is higher than apa? NP apa? NP naught, right? NPA is higher than NP naught. PNB is higher than, yes, NP naught, and PNB is higher than PN naught. Maksudnya, the moment you apply the forward bias, you will get higher concentration of both minority carriers on both sides, right? Kalau you calculate you punya equation tu, time exponential Q VBA over KT, tapi you dapat concentration lower than thermal equilibrium value. So something is wrong somewhere. Either your calculation or your values or something. It's supposed to be higher if you apply forward bias. Okay? So maksudnya you punya value tu should make sense. Right? So that's the conclusion for today. So sekarang kita dah dapat tahu concentration of the minority carrier at the end of depletion region. So this Wednesday, we're going to look at what's happening to the concentration of the minority carriers on both sides in quasi-neutral region, in the next region, right? So basically in this region, right? Region kat sini ni. Okay. So we'll see what happens here next. Quasi-neutral region, right? There'll be another set of equations that you have to use, including diffusion length and stuff, to be able to know the exact minority carrier concentration in the QNR, quasi-neutral regions. Okay. So yes, that's it for today. On Wednesday, I will also tell you about your presentation 1. Okay, presentation 1. So note that you have finished 40% of your assessment, right? So 20% from assignment 1 and 20% from your test 1. So we have another 60% to go from your presentation times 2, 40%, and another test 2. So you've finished 40% and we have 60% to go. Right? Thank you very much, and Yeah, bye for today. Assalamualaikum. Stay safe.